audits and security reviews of software architectures. And at the same time, he's doing his PhD in computer science at the Freie Universität Berlin, working on privacy-preserving extensions for GNU Thaler, and this is also what his talk is
about. Can you hear me well? Yeah. Awesome. So yeah, welcome to my talk. Are you old enough to buy this? This is about work that we did for GNU Thaler, a digital payment system that I will talk later about, and an extension that we did to provide age restriction scheme in a zero-knowledge manner. A couple of words up front. Let me get this not just out of the way. It's important to me to thank the sponsors of this work, which is for a big part the NGI program of the European Commission. Just recently, my company, Code Blau, became member of the NGI Thaler project in a consortium, together with the TU Eindhoven. So we are working on making GNU Thaler a reality in the Eurozone and also in Hungary. And also that was funded in an earlier project with the NGI Pointer program. And also our company is funded by the Federal Ministry of Education and Research. So thank them. Oh, and by the way, also thanks to Tanya letting me. It's very kind, and also for all the organizers of this event. Thank you. So quickly, who am I? I'm doing consultant work since 20 years. I should mention, because the previous slides from previous talks, there were security consultants mentioned that did, let's say, more dangerous and harmful work. That's not what we do. We help software companies or hardware companies to develop proper software and avoid mistakes and so on. That's my take. And as a PhD candidate, the work I'm presenting is part of that, and I'm also part of the GNU Thaler dev team. What can you expect from this talk? I will present you an age restriction scheme in the context of payment of e-commerce, not the general age restriction scheme. That's maybe important to mention, because the very first presentation, or right now the chat control problem that we face, so to speak, our scheme has nothing to do with this and won't be a solution. It's very dedicated to e-commerce payment scenarios, and you will understand why in a bit. So that's what I'm going to present. As a sort of drive-by, while I'm presenting this, there are a couple of things I want to show by example, if you wish. It's like how cryptography can be used, and how certain concepts in it, like zero knowledge, are helpful tools to achieve certain goals. We will see what security games are to prove certain properties, or actually to express certain security properties of a protocol, and also provide an example for security proof. For those who haven't seen those, that might be insightful. For those who are fluent in this, I would appreciate from both groups feedback, because part of the slide decks will become educational material on GNU Thaler at some point. So if you find them useful, please tell me. If you don't find them useful, please also tell me, and maybe why. We won't have time to go very deep into GNU Thaler, how it works. That would be a talk in itself. I'm happy to tell you about it after my talk. And I don't have any demos to show you, unfortunately, but teaser will come. After a quick introduction, I will invite you to a quest for age restriction scheme, and later how it's integrated in GNU Thaler. And we will then go into discussions and conclusions, also in the context of this conference, how far our solution is applicable and relevant. So, age restriction in e-commerce. I make a very controversial first statement by saying there's a broad consensus in society about the necessity to protect minors from harmful content. I think in this statement we can more or less dispute every word, what the consensus is, how broad it is, what the necessity actually means, and what protection of minors or minors themselves are, what the definition is, and what harmful content is. But clearly, with the latest legislations, we see there is at least a legal ground now set in stone, which requires certain kind of mechanisms. So I'm not here to make a proposition that this is good or not at all. I'm just sort of trying to find solutions under the given reality of requirements. For instance, policymakers are encouraged, policymakers in the EU, EU member states are encouraged to provide applicable and useful tools to do age restriction or age verification systems in e-commerce systems. So there's a need, so to speak, to provide solutions for verification in e-commerce. That's taken as a technical challenge. Let's try to find a solution, a good solution. If you look into the right now already available solutions, what we find are basically three categories. One is clearly the easiest to understand ID verification system. You show up if you go to a shop, you show up, you present your ID card, but also online, this is sometimes asked for. Clearly, that's not a good solution. We will compare this to the other ones. There are restricted accounts, meaning if you have, for instance, if you can prove that you are owner of a bank account in Germany, that might be sufficient to prove that you're old enough. This is a mechanism if you buy, I don't know if you're smoking or not, in Germany you can use your, I think it's Maestro card or EC card or whatever it's called. It's a debit card. If you go with this, you can buy from a machine, from a vending machine, your cigarettes, because that is proof enough that you are of sufficient age. So those are proxy systems. These are also breaching privacy as the ID verification, because the vending machine and the provider learns much more than your sufficient age, obviously. Let's say the newest category of so-called attribute-based systems, which try to use cryptography to put them into good use by having very clever mechanism by which you can prove certain properties of your identity without really disclosing it. So it's you get from a trusted authority, you get some sort of a complex certificate from which you can derive a proof, for instance, that you are at least 14 years old, if that is required. And that can be generated in a zero-knowledge way. Systems like that already exist. But especially the last point is they do exist, but they turned out to be not very practical in terms of setup. From a privacy perspective, we could just estimate and say, privacy-wise, the first two solutions are clearly bad solutions. They breach too much into the details of your identity, provide too many informations. The last one, we might say it's good enough without providing you details how they work, but we could believe that they are good enough. But one thing that they all have in common is they require at least an external authority for them to work. And when I say external authority, it's even an external authority outside of the participants in a payment scheme. So usually you are the customer, there's a merchant, and maybe there's also a payment service provider involved. So these are three parties. All these solutions require an additional party, in a sense. And it's our impression that this is not really necessary to make age verification work. We believe that this is a violation of a principle called subsidiarity that I want to quickly tell you about. It's a very old concept which says functions of government, such as granting and restricting rights, should be performed at the lowest level of authority possible, as long as they can be performed adequately at that level. I think I'm in a Protestant country, but this is from Catholic law school from hundreds of years ago. But it's a good principle. I think that's a principle we should apply. So, because we believe that the right level for authority to decide if this is sufficient age or not are the parents and guardians and caretakers of minors, and not some other external authority. So a scheme that wants to be in accordance of the principle of subsidiarity should these people or this group, this level, to set the restriction. So our goal is to design and implement an age restriction scheme. First of all, outside of any particular payment system, just a general scheme with the following properties. It should tie age restriction to the ability to pay and not to any ID property per se. And it will become clear what that means. If you're not old enough, you shouldn't be able to pay. It shouldn't be a result of your ID properties. It should be just you wouldn't be able to pay if you're not old enough. That's what I tries to convey. It should definitely maintain the anonymity of buyers. So in the transaction, whatever we do with our scheme, it should not disclose anything about the buyer. And to be very precise, it also maintain the unlinkability of transactions. So even if one transaction might be anonymous, if I can link multiple transactions as being linked to the same person, that is also not acceptable. And as I described earlier, it should be aligned with the principle of subsidiarity, meaning parents and so on should be the entities that decide whether a child can buy or not. We can debate about that later in the discussion section. And lastly, because that seems to be important in times of blockchains, although the hype is diminishing, it should also be practical and efficient in the way that operates. So let's go. As a teaser up front, here you see a screenshot of a very old version of GNU Tala. It's a screenshot from the web extension in, I think it was in Chrome, where I'm just withdrawing some money from a test system. For whatever reason, the currency is called Rs, but I don't care. And here you see the age restriction already mentioned. So while I'm withdrawing money, I'm able to set a restriction on that particular money that I'm withdrawing. So I wouldn't be able to buy anything else. If I click on under 10, it would mean I'm not able to buy something that is only available for somebody older than that. Okay. So that's as a teaser, that exists. That's what I meant with it's bound to the ability to pay, it's bound to the coins. So here starts our quest for a solution of age restriction. It will be a journey through slightly cryptic territory. In a previous version of this talk, I had basically no pictures, some diagrams. I added some pictures. I hope they are helpful. Guide your intuition. The basic assumptions that we will work with, although we will lift it, or we can lift it later, is let's assume bank accounts in our world right now can only be are only under the control of adults. Children cannot have bank accounts. Let's start with this assumption. From there, the scheme makes much more sense. We can lift this assumption later, but this is the one that we start with. And the basic ideas that we formulated at the very start of our endeavor was to say the guardians are the ones that commit to a maximum age, and that's represented with this. The G figure here is the guardian, and there's a commit function that does something. That's the commitment to a maximum age. We want this commitment generates some data that is then passed on to the child, and the child is then able to attest adequate age, not their age, but the age that is required for the payment, could be a lower age. The result of this attestation is given to the merchant, and the merchant should be able to verify the attestation. And here now it becomes interesting. That was sort of the picture of one transaction being done, if you wish. Now the idea is from a given set of a commitment that the child has for an age, it should be able to generate a new set of commitments, because if it would reuse the same commitments that would be linkable and so on, it should be able to generate a new set of commitments that we call derive, and then use it for attestation. But our system should make sure that the child is not cheating while deriving a new commitment. The payment service provider should be able to compare two of these commitments, the earlier one and the new generated one, in order to ensure, these are compatible. If the money was earlier only up to 10 years old, the change that the child gets is also only up to 10 years old. We need to make sure that this is in place. So that's the idea. In rough terms, that's the scheme that we have in mind. And once we have this, we can iterate, obviously. So after one transaction, the child generates a new commitment. It can then attest for during the next payment step. The merchant can verify, the child can then again derive a new commitment and so on, and this goes on. As you can see, there's no payment yet. It's just a rough scheme that we want to lay out and formulate and eventually implement, and later we merge it with a particular payment scheme. So to plant a little bit of intuition into your minds, I will sort of give away the solution a little bit, not the full solution, but kind of guide your intuition here. Think of these logs that you see here. The numbers are ages or age groups. Usually, probably practically, we will think in age groups, like the ages from 0 to 7 are age group 1 or 0, and from 8 to 10, it's the next age group, and so on. And imagine we have a key pair, or the lock and the key, for each age group, okay? Conceptually. And each of these keys have I don't know if you can read them, there are some random looking data. Those are like unique identifiers, public keys if you wish. And as you can see here, the last one does not have the private key. So imagine in this picture we have 4 age groups. The idea is to have 4 key pairs, except for the last one where the key is missing. There's a public key, but the private key is not there. And if we write down all the list of the public keys with the corresponding age group that they belong to, and we somehow make this an official thing by putting a stamp on it, this is the, think of this as the payment service provider signing this, yes, I believe these public keys are the right ones or good ones. This is what I have in mind when I say commit. Commit will some sort of generate this kind of data. That's the guiding idea. It will be much more clearer later, but this might be a helpful idea. What can I do with this? The attestation and the verification now is something like that. Imagine we have a contract. The contract requires a specific age group, and proving this age group with the data that we just saw, the public keys and so on, I can open the lock and use it only if I have the private key for it. In this case, if you remember, the age group 4 was not available, but age group 3 is available. I can sign the contract. This is the way how this lock is added to the contract, and give it together with the list. That's the list down here. That's a commitment. Give it to the merchant, and the merchant can see there's a lock with number 3 or the age group 3 under this contract, and this contract, excuse me, this public key is listed in this commitment. And this commitment is signed by the payment service provider, so I trust it. Yeah? That's the idea how attestation and verification can work. Again, this is not technical. This is just to guide your intuition for the upcoming slides and more technical part. The last thing is the derive and compare part. That's the more interesting part. And the only picture I have is this one. Let's start with the upper half. You see here again our set of locks and keys. Again, one is missing, and we wish to have a derive operation that is able to generate a new set of locks and keys. And I'm indicating it by sort of extending the lock with a little bit here, and the corresponding private key also with a little bit underneath. That's just the picturesque way. And the idea is that I can do this operation and generate a huge, complete new set of public keys and only the private keys together that I have. And the compare operation now should be able to see, well, here's the old list of commitments that I have. I can look at each number, at each row, and compare that in the new set. The top number is the same as in the old list, and in the new list, the bottom number is the same. Okay? If that is the case for each of the locks, I would, as a payment service provider, then say, okay, I believe this list is an equivalent list to the one before. That's the intuition here. Okay? So these three pictures might be helpful to keep in mind. Now consider that you are a software developer and I'm trying to give you some specification, what I actually mean, except for the pictures, some sort of more specific in terms of what are the data, what is the data that I expect you, that comes in as input and is provided as an output. 5 functions I want you to implement. They will have, the commit function will take in minimum age, that's the A here, some randomness probably, and it should output commitment and a proof. If you think in the pictures before, the Q is basically the list of the signed list of public keys, and the proof are the private keys. Q stands for commitment. That's important to remember for the mnemonics down there might be helpful. The attestation function is also very simple. It takes a minimum age that I have to prove. It takes one of the proofs that I can provide, if that is applicable, and it returns an attestation. The attestation in this case was the signed contract in the picture below. The verify function should take the minimum age, the commitment, that's the list of keys, and an attestation, and calculate a Boolean value. Is that the correct attestation or not? I should mention T stands for attestation. That will also be important for the next slides. The operation takes the commitment that we had, the proof that we had, some randomness, and generates new commitment, new proof, and some blinding that will become important later. The compare function now only operates on the commitments, basically, the public keys, and compares those. It can only compare those if it is given the blinding before, and returns true or false. So we are getting closer to a specification. I now was able to give you some function signatures, and basically the sets that we are dealing with here abstractly should be large enough to not prone to exhaustive search and so on. Other than that, not much like relationships are required. And of course, we still need to sort of define basic properties of these functions and the security requirements, and we will do so. Now we have this scheme in like very abstract terms. The players are the guardian, committing to some age, giving some data to the child. The child can attest the minimum age and provide the merchant with the minimum age, the commitment, and the attestation. The merchant is able to verify that. After that was successful, the child can derive a new set of commitments and a proof along, and can ask the exchange to compare that to make sure that this is the compatible set of commitments. That's the scheme that we now were able to sketch. And the beauty of this approach, I would say, is that already on this level, we find a problem in the protocol. Because the derive and compare operation will be done iteratively. Iteratively in the following sense, the child will start with one commitment, will do the payment process, will derive a new commitment and let the exchange compare that. So the exchange will eventually see a whole sequence of commitments that, by comparison, all belong to the same sequence. It can, because the compare operation only says true if two commitments belong to the same derive operation. So in other words, the exchange is able to identify the sequence of derive operation. It would come from the same child. So with this naive approach, the unlinkability would be broken of the system. So we must avoid this pitfall here. The way to do this, to solve this problem, is to use a zero-knowledge version of what we have so far. So we stick with the ideas, with the 5 functions that we have, but we substitute the simple call of commit and compare by embedding them into a zero-knowledge protocol, or what we call a cut-and-choose protocol. I gave it the name derive compare kappa. You will see why. And again, as a sort of hopeful, helpful picture, what we do is we start with one. For a second, in the pictures before, we had multiple locks that we dealt with. Just assume we start with one of those. Yeah, let's say the first one. That's the lock number 1. And what we do is we derive not only one new lock, we derive 3 of them at once. So for each of the locks that we had before, we derive 3 of them at once. And what we send to the exchange is the original data, the original commitment, together with what I try to indicate here with these colored circled, overlaid circles, is sort of a fingerprint of our new set of locks. Okay, that's what we give the exchange. The exchange then randomly chooses, in this picture, a color. It would choose a number by random choice. And we are then supposed to give it the derived keys that the derived locks in this case, which are not this color. Everything but this color. And now the exchange is able to do 2 things. It can check if from this, if this original lock and this lock, if they are comparable. It can do the same with the other one. And if they are both comparable, it will probably trust that the third one that is not being seen yet by the exchange is probably also a trustworthy, comparable commitment. Does that make sense? So if that is the case, here we indicate that the exchange is sort of trusting the final one being the right one, a comparable one, but of course with a caveat that we will talk about in a second. So that's a maybe helpful picture. Let's go through it a little bit more in a systematical, technical way. Let's say we have a kappa. Kappa technically can be any number greater than 1. Probably will be 3, as in the picture. And what we do is, for each of our commitments, or for each of our locks, for each of them, we generate kappa many, together with kappa many blindings, and we call on each of those derive. So that's the first operation as in this picture. And what we then do is building a fingerprint of all blinded fingerprints of all these locks. That is sort of this circle here that can be deduced from these things, but not backwards. So it's a hash of blinded hashes concatenated. And that's what the child sends to the exchange. So the original commitment together with the hash value for the next ones. The exchange can then choose randomly a gamma value between 1 and k, that's represented here as the green circle, and the child then has to reveal. It has to reveal all the new generated commitments, those are these things, together with the blindings that were in use. But the sort of the middle empty section, that's just the blinded hash. So it will not reveal this commitment, it will just reveal a blinded hash of it. What can the exchange do with this? It can recalculate this value, the original hash value, by really doing the hash calculation here. But for the gamma, it has to plug in the given blinded hash. It cannot generate that, but that's fine. If this turns out to be the same H0, the commitment was correct, and it also can compare each of the unblinded revealed commitments, new commitments, that they are actually comparable. And if so, implicitly in this protocol, the unrevealed derived commitment is the new commitment for the child. Okay? So, mind you, we still need to have derive and compare as functions, but we can embed those into this cut and choose protocol and gain the following properties. With this protocol, the exchange, the payment service provider, learns nothing about the unrevealed commitment, the new commitment. Also not even the hash value of it, because the blinding was also involved in doing the hash value. And it will trust the outcome of this protocol with the chance of kappa minus 1 over kappa. So in the case of 3, it would be a 2/3 trustworthy result of it. Or in other words, the child would have a chance to cheat with 1/3 in this case, if kappa is 3, right? So because the child could generate maybe a commitment to a much higher age, and if it's lucky in 1/3 of the cases, it would be able to cheat with this. So if we want to have a higher certainty, we would raise the value of kappa, but that's basically just a parameter here. We will come back how to improve this data. So what we gained is we have guaranteed unlinkability now in our scheme, but for the price of an adjustable uncertainty. Okay. By the way, this is similar to the way how GNU-Tala does a refresh operation, where you, after you purchase something, if there's any remaining rest value on the coin, you can ask the exchange for change for this thing, and it will go through a similar process for getting new fresh coins that are not seen, not known by the exchange. And again, mind you, we still need to find proper implementation solutions for the derive and compare operation. Okay, so we end up with a slightly refined scheme. We have the same players. The guardian commits to an age, gives the child a commitment and something to prove. The child can make an attestation for a minimum age, if applicable, with the proof that it has, passes the result, the attestation and the commitment to the merchant. The merchant can verify with this data that this attestation is sound, and the child can now perform the derive compare zero knowledge protocol in order to gain, derive a new compatible commitment. That's what we have. So far, so good. If I would ask you as developers, please start implementing something, you could just return true, for instance, for every verification call. That would be, in a sense, compatible with all I've said before, but it's not what we have in mind. Of course, these solutions should be sensible, so we need more requirements. The requirements that we want are, first of all, very basic requirements. It should do the attestation as it is meant to do. It should not return true in cases where things are not properly, it's not the right minimum or attested age and so on. Those are the sort of easy requirements we can formulate. Very formally, I'm not going to bother you with that. Like formally meaning based on the signatures of the functions that we have defined so far, mathematically, we can very precisely define what we mean by these basic requirements. The attestation should exist, there should be, the efficacy should be given, and so on. The more interesting ones are the security requirements. And the way that we formalize those are by security games. Meaning, we will define the requirement, for instance, in usual terms, the unforgeability of a minimum, meaning that the child is not able to forge an age that is not committed to by the guardian. We will define what this requirement means by defining a game that we call forging an attestation, a very specific set of steps that are performed between an adversary and the game master, that winning this game with a probability that is higher than a half, we will call being able to forge the attestation. I will give you an example. So the requirement for unforgeability of a minimum age, we will formalize by through the medium of a game, forging an attestation. Similarly, the non-disclosure of age, that's the privacy part, meaning that the merchant learns nothing about the actual age of a person or the committed age. It only learns about sufficient age. If somebody has, let's say, has up to age group 4 and the purchase requires only age group 2, the only thing that the merchant would learn is, well, it was old enough to provide me proof for 2, but not whether there's a higher value or not available. And we define this very precisely by a game that we designed called age disclosure by commitment or attestation. Basically a game in which the adversary, which is now represented as being the merchant, but also the exchange, both can be considered adversary. They get all the data that is generated by this process so far, and they should not be able to detect the right or guess the right age by other than chance, depending on the size of your age groups, obviously. If you have only one age group, it's not difficult to guess to which age group you belong, right? So it depends on the size of the age groups that you have in the system. And the final one, that's again a privacy thing. The unlinkability of the commitment and attestation will also be defined by a game that we call distinguishing derived commitments and attestations. And this is, you can imagine, assume we have two children, let's say, that use this scheme, and each of them generates commitment after commitment, attestation after attestation for like a long, each of them has a long chain of these data trails. And imagine they are equally long, and the game master randomly takes 2 elements out of these sequences, just at random positions, and gives one of those, again, randomly chosen, one of the taken out elements to the adversary. And the adversary has to decide to which of the sequences this data belongs. If it's capable to do so with a chance higher than a half, just guessing which one, then we would say the adversary has won the game and has broken, or the unlinkability wouldn't be given. So if you come up with an implementation of the functions that we have, we would start playing these games, and if I start winning more than 50% in the last one, I would have shown you your unlinkability is not really there. You break the security requirement. So, and we mean that the requirements are met when an adversary in each of these games can win those only with negligible chance. I should also say that what we mean by adversary is somebody, any algorithm that operates in polynomial time, and probably also some space restriction should be put. And I want to give you one example. Again, this is going to be material used for education purposes. Why not trying this out at you? The game Forging in a Test, the simplified version of it, is like this. We start by choosing, the game master is choosing a random number from our age groups, so to speak, one of the age group values and some randomness, and makes a commitment out of it. That's like the role of the guardian. So out comes a commitment and a proof. And the adversary is given this age, the committed age. It gets the commitment and the proof, like consider this being a child getting all this data, and it is supposed to generate another age, a minimum age in the attestation, but the only solutions that we would accept from this adversary here, from the child, is when the age is actually larger than the committed one. That's what we want to try to win here, right? The child tries to win. The parent has said you only are allowed age group 1, but this is age group, he has to show that he can generate something larger than age group 1. The question? Or, oh, 5 minutes. Oh, I see. Really? Okay. Let's go. they win. So we just take the data that we got from the adversary and start to verify on it and see if that is true or false. And the adversary wins this game if this is returns 1. And the idea is only if you can, the requirement is then formulated then for any conceivable allowable adversary in polynomial time with this signature, the probability in this game should be negligible. The epsilon is usually non-zero and depends on the security parameter that I have left out here for simplicity, but it should be basically not winnable by the adversary. So our task is to find, now that we have the requirements, implementation or an instantiation of these 5 functions that meet these requirements. And I will quickly present you the solution to this quest, which is based on ECDSA. You might have maybe guessed it already from the pictures if you are familiar with this. And basically, to as a again guide the picture, the commitment picture that we had earlier. Those are really key pairs, public-private key pairs that they are generated in the commit step, and the private keys are simply dropped that are not acceptable for the group. So this is a one-to-one correspondence. And the commitment then is just a set of public keys, and the proof is just a set of allowable private keys. So far, so good. That's what the guardian gives to the child. The attestation and verify, again, is then simple. The child has all of the public keys, just a couple of the private keys, and the attestation is simply signing the contract with the right key, obviously, and the merchant gets all the public keys and the signature and can verify that this signature is made with the corresponding private key or public key for that matter. So far, so good. The more interesting part is the derive and compare. That was the more elaborate operation. How can we do this? And elliptic curves come with nice linearity properties in conjunction, or for this ECDSA scheme, it's easy to formulate. That's why I have it here. The child has, again, the set of all public keys, some of the private keys. It chooses a random value, scalar value beta. And what it can do is, with the public keys, it generates a new set of public keys. I'm claiming they are public keys, but you see it's an operation, a scalar multiplication in the elliptic curve, just moving beta times forward with each of the public keys. And it can do so independently with the private keys as well, just multiplying modulo the group size, the private keys with the same beta. And the result, so you have do this with the public keys, you do this with the private keys. The result is, again, corresponding private public key pairs. That's the beauty of the elliptic curve algebra that we have available. So that's the way how a child can derive the new set and private keys. And the compare function is easy. Again, what does the exchange get? It gets the set of original commitments, the public keys, and the new ones, and the blinding, that's why we need it here, and can compare if it does the calculation itself, that it ends up with the at the right points on the elliptic curve. So that's what we have. And I claim this scheme meets all the technical basic requirements, but it also meets the security requirements. I wish I could show you the proof, because it's very easy. I do it over the coffee if you're interested afterwards. Let me quickly show you how this scheme is now integrated in GNU Tala. GNU Tala is an online payment system where the basic ideas go back to Chaum's blind signatures in RSA. It's a payment system that is taxable. It's free software, it's efficient and privacy preserving, unlinkability and anonymity guaranteed for the buyers, not for those who sell. Those are taxable. And in the scheme, By the way, the participants are the same participants in the payment scheme. That's why they show up here. It's, again, the customer, an exchange, and the merchant. We just add the component of a guardian here. The way how coins are represented in the scheme are public-private key pairs, but for a different crypto scheme. And they get their value from the exchange by the exchange signing the public keys with a specific denomination key. The exchange would have denomination keys for, let's say, 1 cent, 2 cent, 8 cent, 16 cent, and so on. And if I come there with a public key for a coin, it would sign with a particular denomination key. That's how the coin gets its value. So it's the public key together with the signature. And the verification is then a signature check. The way how to now bind our scheme with the payment scheme, sort of link a coin with the commitment for an age together, is to simply require, when here originally the payment scheme would blindly sign the hash value of the coin, it now just signs the hash value of the coin together, concatenated with the hash of the commitments. So it does a signature of this combined thing. So that's how we tightly bind the age commitment to the particular coin. And we do this for each coin. And also then, obviously, the signature check, the validity of the coin, is then requires that somebody provides the commitment, at least the hash of it. That's how we do this. And then, from a protocol perspective, it's just a matter of overlaying what the Thaler system does with what our scheme does, and they are very well in conjunction. You see all the steps that we had with the commit attest, and here to show after the attestation for purchase, the purchase part of the Thaler protocol is then just augmented by the data with the attestation. So the purchase itself does not change, except it gets added additional data, so the merchant can sort of do whatever it does. It's the deposit, what it then does in the Thaler lingo. That's when it transfers coins to the exchange and get monies to its own bank account. But at that time, it can also do the verify step. That all lines up very nicely. And also the refresh protocol, which is needed if you have any remaining rest value on your coin, you can ask for change from the exchange. That's when we have our derive compare operation to make sure that the next new fresh coin that the child gets is also have the same equivalent age restriction bound to it. That's basically it. Nice. And then again, this is the where we are at. If I have time, I would go into the. We have no time. Okay, for discussions and the conclusions, which are actually the most important part, obviously, for this conference, I'm happy to talk to anybody who's interested outside afterwards. And there are a lot of aspects we can talk about. Thank you for your.
Yes, thank you. So I can hear that already, that you can hear me well. So as Andy said, yes, I work in post-quantum. So today I'm going to give you like an overview of what this means for me. And let's start with telling you what it is. Okay, so when we give the definition of post-quantum crypto, it's it's a crypto that is implemented on a classical computer, but it is resistant to attackers, even to attackers that have a large quantum computer. Okay, why do we make this distinction? Because the public key crypto that we have deployed today in the world is actually not resistant to attacks on a quantum computer, specifically because these problems, factorization and discrete log, they're the underlying problems of our current schemes, and for them we have what we call the Shor's algorithm, which is a quantum algorithm that runs in polynomial time. So this means that we need to replace all the public key crypto that we use. And so it is really about public key crypto. So I mean public encryption, right? Public encryption in public key crypto, it just means encrypting your key that you want to exchange. So key encapsulation mechanisms, CAMs. And then another big area there is the signatures. And there are some other things that we want to do, but we are very focused on these two for now. So on the side of symmetric crypto, well, the picture is a bit, it is less dramatic, the impact of quantum computers, right? We have this Grover's algorithm that has a quadratic speedup over the regular exhaustive search, but quadratic speedup means that you need to double the key sizes. So there is a easier, we don't need to replace anything. I do want to argue still that this is a problem for everyone. Because when you think about it like any infrastructure, it starts with the handshake, it starts with the exchange of a secret key. And so then if your handshake is compromised, then the entire, everything that follows is also compromised. So that is kind of like the usual pitch that you get for post-quantum crypto. I do want to give you an alternative view today, right, or to tell you what this means, what post-quantum crypto means for someone that works in the area. And to me, it really means it is a study of hard problems, okay? Because when you have a hard problem, you have a public key crypto system. And what I mean by hard is specifically computationally hard problems, okay? So problems for which the best known algorithms are exponential in time. Here I have some nice problems on the slide, so that they're not all problems that are used in crypto. So for instance, these that are with light blue are not used in crypto because it's not enough just to have a hard problem. It needs specific properties. Here in red, you have the things that you know, factorization and discrete log, which are classical crypto. And then I also have some problems that are used in post-quantum cryptography, so that are hard even for a quantum computer. And so you might be thinking like, okay, what is so special about these problems that they are even for a quantum computer, right? Or at least this is what I was thinking before I go into this field. And I think the answer to that is really that quantum computers are not almighty. They're just know how to do very specific things very, very well. Okay, and one of the specific things that they know how to do is this period finding, and you have this period in the discrete log and the factorization problem, and so that's why you are able to break them. So in a sense, it is more like these two problems are very specific and not all of the others that are post-quantum, at least in my view. And it just so happens that we have built, all of the crypto that we have built until now is based on these two problems. Okay, and so, yeah, very unlucky coincidence, right? But now we need to replace everything. But when you go even deeper in the field, you understand that it's not a coincidence at all that we have based our crypto on these problems, because that very same structure that actually makes them vulnerable to Shor's attack, it also makes them very convenient for cryptography. The discrete log, for instance, is just amazing, right? It has very small public and secret keys compared to the security that you get for them. It's commutative, it gives you key exchange, it's hard on average, it comes with pairings. So it is all these are things that we have taken for granted until now. And it is very kind of hard to replace them now. So that is what we're doing every day, just looking at different problems, adding some structure to make them better, smaller, nicer. And then if the C of the structure gives you some attacks. Okay, so I did make the pitch of even beyond quantum computers, it is not a good idea to put all your eggs in one basket, especially if your basket hides a serious kind of problem. So that's what I'm going to do in this talk. I'm going to first tell you about what we call the 5 families of post-quantum crypto, just to give you an idea of what these mathematical structures are. And then I'm going to show you an example of a cryptographic design, because I keep repeating how a hard problem gives you a crypto system. Then I will kind of concretize this with an example. And then if we have time, I'll go a bit over the timeline of what we have been doing. Not so much the timeline, but just to give you an idea of where we are now in the timeline of standardization. Okay, so let's start first with the fun part, the different flavors of PQC. So maybe you have seen these 5 areas. It's usually like these different problems. We kind of categorize them a bit so that we know what we're working with. And the way that I will approach this is that for each of them, I will just tell you what the structures are, tell you about a hard problem in the area, and then I will tell you how you can brute force this problem. Okay, I won't have time to go into cryptanalysis concretely, but I do want to tell you how you brute force a problem, because I believe that if you know how to brute force a problem, you know what the problem is going to do. We're going to start with something, something that you're very familiar with, hash-based cryptography. And yes, we are in public key crypto, but you're used to hashes from symmetric crypto, right? You have this hash function is this function that is supposed to mimic a pseudo-random function. It takes some arbitrary length input and it outputs something of fixed length, so what we call a hash at this end here. And you know the hard problem there is to find the pre-image of your hash, or not the only hard problem, but let's say the one that if you break this, you break everything. And that one is very easy to explain how to brute force. You just need to try for all of the combinations. And you can actually build signatures from hashes, and it is very nice because the security is very well understood. And one very nice thing about them is that these digital signature schemes that are built on hashes, they have only one security assumption, right? You only have the assumption that your hash function is secure. And all of the other schemes, they have some problem plus a hash function because they do need to use a hash function protocol. So it is kind of an unbeatable argument in terms of the security. And as I said, yeah, you 2 to the n for brute forcing it. Then we have what we call multivariate cryptography. So multivariate stands for multivariate systems of equations, right? We have systems like the one here in the example, so a system of equations with some variables, and your goal is to find a solution to this system, right? Finding a solution is finding an assignment to all of these variables that kind of makes all of these equations equal to 0. And you know that this problem is very easy if it's a linear system, right? You have Gaussian elimination and you just find the solution. When you go up a degree, as soon as you have multiplication, the problem becomes very hard. So that is a hard problem that we use. The way that you brute force it, it's the actual brute force that you're familiar with. So like the binary search tree, if your system is over the binary field, which this one it is, otherwise you generalize that. And the way that this works is that you give an assignment to all of your variables. So let's say first you assign them to 0, and then you evaluate all of your polynomials and see whether they all satisfy the requirement to be equal to 0. Here they don't because of the second one. So then you need to go back, give another assignment to the last variable that you did. Try that one. If it doesn't work, you go with another example. And then, so this actually kind of builds you like the depth first search in a binary search tree until eventually you find, oops, sorry, I missed the solution. Until eventually you find something that is a solution to the system, and then you have one. And the complexity of this exhaustive search is, of course, 2 to the n if n is the number of variables, or q to the n if you know you're over a bigger field. Okay. So then the next type of crypto we have is this code-based cryptography. Code-based comes from error correcting codes. So it is a different field, right? But crypto has then stolen some ideas from it. So it is a field where, yeah, you need to kind of, you want to be able to correct errors that maybe happen on the transmission channel when you're sending messages or when you're receiving messages from a satellite or something. And then for this, we have error correcting codes. This is what the code looks like. Let's say you have this what we call the parity check matrix, this H here, and then you say that some word, so some vector, is a code word if it is in the kernel of this H. Okay, so if you multiply H by your word, it gives you 0. That is a code word. Otherwise, it is not. It is outside for code. Okay, and then if it is not, it means it has some error, maybe a small error. So it means that it's not just a code word; it's code word plus some E. When I say small, I mean that the number of zeros in this vector are small, is small. So then we call that the Hamming weight. And then the way that we use this in crypto is that we intentionally add this noise to a code word, and then the hard problem would be to kind of decode this and recover the code word. So what happens is that, yeah, if you kind of rewrite this, you will see that because these are linear codes, and so so you get 0 plus H times your error vector equals something. This something we call a syndrome, and it is kind of like how far your code word is from how far your word is from proper code word, and this is what gives us the hard problem. So what we call the syndrome decoding problem. If we are given, or yeah, I will write it more visual like this because it's easier to see. So you are given this H, which is the matrix that describes your code. You are given this S, and you need to find an E, this vector here in the middle, that satisfies this equation. Plus, also it is of low Hamming weight, meaning it has very few very few non-zero elements. And let me tell you just briefly why this would be hard, because it doesn't look like it on the first look, right? If you just want to find some vector that satisfies this, well, this is easy. It is a linear problem, right? There are many solutions to this. So you can describe it algebraically, and it's going to be linear. But then there is a second constraint. That was the weight constraint. Okay, you also want this to be of small weight. And so, yeah, finding an E that satisfies this is easy. Finding an E that satisfies the weight constraint is easy, but finding an E that satisfies both at the same time is hard, and this is what breaks the linearity. Okay, how can we brute force this? Well, if you think about how what this means in terms of matrix multiplication, well, you see that here you multiply the first row with the E to get this first element here. Okay, so it means that only those columns that correspond to entries in E that are equal to 1, only those kind of matter in the multiplication. All of these other columns that I've left don't really matter. So kind of this S vector is equal to the sum of these columns, the columns that correspond to the non-zero coefficients here. Okay, so then to just find, since this is the case, to find, I don't know, your E vector, what you need to brute force is which columns are taken to sum up to S. And so then it means that you pick randomly columns until you do this. And what is the cost of choosing this combination of columns? Or it is n choose t, right? If I know that t is the number of columns I need to have, and there are n in total, this is what I need to, combinations that I need to try. Okay, so that is one problem in code-based. Now we go into lattice-based. So you see, lattices are these grid of points that you usually see around when you, and they give very nice pictures, so you might have seen them. More concretely, it is a discrete subgroup of your Euclidean space. And why do I say discrete? Well, yeah, here the dots that are on the picture are points on the lattice. It says discrete because it means that around every lattice point you have this ball of empty space that doesn't touch another lattice point. Or maybe it's easier to see it with the description of the basis. So if I tell you, well, a basis for a lattice is just some vectors, linearly independent vectors. So here I drew everything in the two-dimensional space. So let's say this is a basis for this lattice. Here this vector 4, 0, and here this 3, 5. I did approximately, but you can see. And then you say that a point on a lattice is any integer combination of this basis. Okay, so it has to be integer coefficients in the linear combination. So if any point here that cannot be written as an integer combination of these two is not a point on the lattice. Okay, so that is a lattice. What is a hard problem there? Where, for instance, you have the closest vector problem, which is if I give you some point in the Euclidean space, so this point here, for instance, it is not a point on the lattice, find the lattice point that is closest to it. And here, this would be the solution. Okay. So I'm not necessarily going to brute force this, but I'm going to show you like why this is hard. So for instance, if you have something that we call a good basis, this is like the blue one on the left. And it is good because, well, usually if it's short vectors that are very orthogonal to each other, that's something that is kind of like a good basis. Here, one way that you can solve this problem, let's say this is your target point here. One thing that you can do is first write this point in terms of your basis. Okay, so yeah, I've calculated here that this point is equal to minus 1.4 times the first vector plus 2.2 times the second one. And you can see immediately that it is not a lattice point, right? Because these are not integer coefficients. What we can do, because we want integer coefficient, well, let's say a first naive idea is what happens if I round this up? Will I get to a nice, will I get to the closest one? And here it was the case, yeah, you actually found the solution, the correct solution. If you do the same thing with a bed basis, so this kind of describes the same lattice, but the vectors are not so orthogonal. If you do the same thing, I did it again with the combinations, I did the rounding, and then this gives me this point here, which is farther. And in a more bigger, this is just two-dimensional, so it seems like an easy problem. But if you go to higher dimensional lattices, this really becomes hard. And going also from a bed basis to a good basis is also a hard problem, so that's why we can't solve it. And finally, the fifth family that we have is this isogeny-based cryptography. And I'm going to try to make it, to show you something that you're more familiar with, so the elliptic curves, right? This is kind of like a picture of an elliptic curve that you have seen before. So it's an algebraic curve that we usually draw like this because that's kind of the shape that it has. And you have points on this curve, and you know that you can multiply points by some scalar and to get another point on the curve right here. And this is what gives you like the discrete log for the discrete log problem. That is a classical crypto problem, not post-quantum. Okay, so if you're familiar with this, I will try to make you look at this point, this color multiplication on points as a mapping, right? You're mapping a point on your curve to another point on the same curve, okay? And these are the equations that for instance, describe this mapping of multiplying the point by 2. It doesn't matter what the formulas are, but you can see that it tells you where does x go in the other point and where does y go on the other point. So then an isogeny is going to also be a mapping, but just the only difference is that instead of going from a point on the curve to the point on the same curve, it goes from a point on the curve to a point on another curve, okay? And yeah, like here in the photo, and then it is not bijective. You see you have several points that go to a same one and so on, and it still has some formulas, albeit more complicated than the previous one, but it's still a mapping, okay? And the hard problem here is if I give you these two elliptic curves and you need to tell me what the isogeny between them is, so that's going to be the hard problem. To tell you how we brute force this problem, I need to tell you 3 more things about isogenies, 3 properties. So first, the degree, okay? So the degree is some property of the isogeny that tells you how big it is, okay? Why does it tell you how big it is? Because the complexity of computing it, so not finding it, not a hard problem, but even just computing it, is linear in the degree. So if you have some exponential degree, then it's going to be very hard to do. But you also have these properties of second thing. The degrees multiply when you compose isogenies. And this is kind of a way for us to compute a big degree isogenies if it's a smooth degree. So here, if you need to compute an isogeny of degree d, and d is equal to, I don't know, some small primes multiplied together, then you can just compute first, an L1 isogeny, then another L1, depending on what this exponent is. So you can compute them all in order, and since the degrees multiply, eventually you will get to a d degree isogeny. A third thing you need to know to get to a brute force algorithm is that, from a curve E, I know that there are L+1 isogenies of degree L, okay, for L prime. Okay, so now you can see how we brute force it. If I give you this problem with, I'm giving you this curve E, I'm giving you this curve E prime. So then how do you find the isogeny? Well, you can start guessing, right? Here from E, you will have 3 options. You guess one of them. Then you have only 2 options because the third option is going back, actually, and so on and so on. So this is also like a binary tree, but just, I drew it the other way around. So you need to kind of, do all of these combinations. And here at the leaves, you just compare, is this my curve E prime or is it not? And the complexity of this is 2 to the E if that's the degree of the isogeny. Okay, so we're done with the schemes. You know, not the schemes, the primitives. You know a bit how they look like. I promised you that I will give you an example. So what I decided to give you today is this Fiat-Shamir construction because it's kind of like a very easy and fun thing to understand. And the hard problem that I'm going to use here is, another hard problem. By the way, this is in code-based crypto, but you will not know why it is code-based today because I stripped away a lot of the details. But let's say we're working with this 3-tensor object, which is kind of just a cube, okay? This is a cube, and each entry in the cube contains some number, okay? And then you take this cube, and you do a linear transformation on all sides. So it means that you do a linear transformation by this matrix here on the left, and I will show you permutations because that's something we can actually draw otherwise. But imagine that it is any linear combination. So A multiplies on the left, so it does permutations on the rows. Then B multiplies on the right, so it does a permutation on the columns. And then the third one, T, does permutations of this third dimension. Okay, and this gives you another cube, another 3-tensor object. And then the hard problem would be if I give you 2 objects like this that are equivalent, can you find what are these 3 matrices that brought me here? Can you find what is the mapping that brought me from one cube to the other? Okay, so that is our hard problem. The way that we will use this to build a signature scheme, concretely, first we will go through an identification scheme. Okay, so that just means that I will be able to prove my identity, and specifically I will prove that I know the secret. Okay, here the secret is this secret transformation A, B, and T, and the public key are these 2 groups. Okay, so I need to prove to someone that I know my secret, but I cannot reveal my secret, of course, because then you will not be able to reuse it. Okay, so what we do is first we do a commitment, or for Özgür, commitment. So the commitment looks like you pick some random other map, some ephemeral map, and you go to another cube object here. And you commit to this object, to this 3 tensor, okay? And then see, if you look at this, you see that you get a triangle, okay? Because here you have the mapping, your secret map. Here you have your ephemeral map, the one that you just came up with. And here you also know how this object, so your second tensor, connects to your ephemeral tensor, because you can just follow this map the other way around. You can do the inverse of this, get here, and then compose it with your ephemeral map, and then you get this. Okay, so if you know the secret, you know all 3 of them. Okay, this is the triangle that we're working with. And the way that the scheme is going to work is, we have this prover and verifier scheme. And the secret key is this ABT, and your public key are these 2 tensors here, these 2 cubes. So as I said, first you commit, make up some ephemeral map, and you commit to it. Then the verifier will give you a challenge, which is either 0 or 1, and then you will give a response. What is the challenge? So the challenge is, if the verifier gives you 0, then you need to tell them what this map is, the ephemeral one. If they give you 1, you need to tell them what this other thing is. And as I said, this proves that you know the secret, because if you're able to answer to both, it means that, you can also derive the secret from this. Okay, so it kind of proves your identity. Why do we go through this, challenges, giving the one or the other? Well, you can try to think about how you can cheat. Okay, you can prepare for if you know in advance what the challenge is, right? If you know that the verifier is going to ask you for 0, then you just invent this, you do the protocol as normal, you invent this ephemeral thing, and you know it, you can send it. If you know that they're going to ask you the second one, you can also prepare, because you just prepare something from this cube to another one, wherever, and then you can also cheat. But you have a 1/2 possibility of cheating, and then we just repeat this protocol enough times so that we are convinced that the prover has a very low chance of cheating. Okay. And then from this, well, it's just an identification scheme, right? Our goal is a signature, so we make it interactive in a very simple manner, but a very clever transformation. Instead of using the prover to get the challenges, we just hash, okay? And specifically here, okay, same thing about the secret and public key. So we just hash the message and the commitment, and then that will give us the challenge. So if the first bit is 0, then it's challenge 0, otherwise it's 1. And we cannot control what the hash gives us, so, like why the prover cannot cheat. And on the verifying side, it's, you just verify that everything was done correctly. So that is kind of like how you go from a hard problem, specifically from an equivalence problem, from some mapping, to a signature scheme. Okay. Now, about the timeline. Well, I put in the NIST standardization timeline because it is the most famous, let's say, standardization process. And the way that this works is that, in the fall of 2016, they put out a call for proposals. Okay, so just ask for people to submit schemes, and that might be chosen for standardization. And then we went through 3 rounds of, assessing the security of those. Some schemes go to the next round, some are broken, some don't go to the next round because, they're not compact enough, or so on. And we went through 3 rounds first, and then at the end of the 3rd round, there were some schemes that got chosen for standardization. So for instance, we had 1 CHEM, the Crystal Kyber, and then we had 3 signature schemes. So these are, Kyber is lattice-based, and then these 2, Dilithium and Falcon, are also lattice-based, and Sphinx Plus is a hash-based one. Okay, and then the process didn't stop there. We went into a 4th round. Some of the schemes that didn't yet get standardized but are still considered went to the 4th round. And there was also an additional call for signatures, because I think maybe NIST believed that we don't have enough variety in the signatures, or because they wanted a multivariate one. But anyway, there was a call for maybe additional proposals for signatures, and that is the thing that's happening mostly now. The more current thing. And these are the proposals that came in for the new signatures. I've kind of made you a table with how they classify in what we've seen today. So which of them are lattice-based, code-based, multivariate, isogenous. This is symmetric crypto in general, not just hash-based. And these are other problems. So for instance, some, for the min rank, I didn't, allow myself to classify them, but some of them might go into these other categories, but they're considered other. Okay, so finally, why so much variety, right? Why all of these schemes? Well, for that, I need to tell you about the challenges, right? Because our first, as I told you, it is very challenging to find something as good as the discrete log. Okay, we have all of these primitives give schemes that are not so compact. They have huge, either public key secret. We don't have a good substitution for everything. We have schemes that are good for one use cases, for some use cases, schemes that are good for others, but not something that is good for everything. And the biggest challenges are, let's say, first we start with the security assessment. So it is a lot of new problems sometimes it's very old problems, but they have some added structure to make them smaller. So then we need to thoroughly investigate the security of this, and that is kind of like a big challenge. Specifically, it has happened that even some schemes get broken, even severely broken in the later rounds, in the third round of the competition. And here are two examples of those. For instance, here it was a case of a scheme that is based on something that is still being secure, that is still secure, the UOV, but it had a lot of added structure to make it smaller. Here it is a case of another challenge that was, that we responded to. For instance, it's a scheme that is also still based on a problem that is hard, the isogeny pathfinding problem, but with added structure so that you can make key exchange, which is something that we cannot do. And then even beyond the security, then the next, why do we do all of these things, adding structure and so on? It's because it doesn't fit. So everything that we have in post-quantum crypto doesn't fit with our current infrastructure of the schemes that we have, so the TLS packets and everything that we want. And also another very big challenge that we're currently working on is this physical security assessment. So what I mean by this is if you assess the security of embedded devices, right, and then you give the assumption that the attacker has physical access of the device, so they can do, they can do some measurements while the device is computing on sensitive data, measurements like time or, the temperature and stuff like that, and then try to infer something from it. So this is a completely different thing. Even if your scheme is secure, it might not be secure when you have access to the device. And this also makes things more challenging because it fits even less on these devices. And then finally, also we have this challenge of building the advanced constructions that we just cannot do because we don't have the discrete log anymore. So that's also kind of very hard. Okay, so I hope I spent this time telling you what we kind of do every day and what's happening in post-quantum crypto. Thank you for listening. And so now I will take some questions if you have some.
Thanks a lot for the talk. I think we have time for a single question that does not take longer than a minute to answer. I think we have exhausted our audience.
Yeah, they're waiting for drinks. We can also, there's someone there. The last one of the event.
So you say you have to do all these other things because it doesn't fit.
Yeah.
So rather than interpret, I got to ask them what the cables in the packet.
Yes, so that's why I said there are some use cases where you can choose that I want top security, I don't care how long it takes, and then you can use something like classic Michaelis or, something that is big but is secure. For some use cases, you just can't. I mean, you can, they switched around the TLS to make things. Imagine a server that gets a lot of requests, so there's also computational time. And these devices, these embedded devices, they're also like very small. So it is an added cost. It's not impossible, but it is an added cost for companies, for everyone, and it just makes things less possible. And we're used to having it good with the few gigabits more, that is a lot. Yeah, but it depends on what you need, right? It's it is a lot more in terms of 10 times more than a elliptic curve case. I don't know, but we're trying to make things practical. It's always between practicality and security, of course, and if something is too slow or companies find that very costly, they just won't implement it. And we want crypto to be not just secure, but also implementable so that people will actually use it.
Thanks a lot.